In general, with sequential networks, SELU, YELU, leaky RELU, TAND, logistic. If prediction time is important, use leaky RELU. Most used RELU. To compare the convergence speed of the SELU and ReLU activation functions, we will train a classification model on the fashionist dataset using only 5 epochs. It can be seen that using the same number of neurons and training for only 5 epochs, the SELU activation function achieved a higher validation accuracy, 0.79, compared to ReLU, 0.71. About the batch normalization, there are 2 ways to put it when training deep learning. First, before and after each layer. And second, before the activation function. Gradient clipping is a technique that limits the magnitude, or norm, of the gradient to a certain range, specifically to prevent exploding gradients. This technique is particularly useful in RNN where backpropagation can suffer from vanishing or exploding gradients, unlike CNN where batch normalization is more commonly applied. There are 2 ways to limit the gradient within a certain range, clip value and clip norm. For example, we have 2 models A and B. Model A predicts pullover. Model B predicts t-shirt. Transfer learning, train and save model A, then transfer to model B. Train and save model A. Train model B itself. Use model A to train model B, clone model A to model A_clone, and copy the weights of model A to model A_clone. Freeze the layers and train the model for 4 epochs first. Then open it and continue training for 16 epochs. Accuracy is improved more when using model A to train model B compared to directly training model B, 93.5% greater than 90.95%. Transfer learning works best with deep convolutional neural networks due to their ability to extract useful features from data. In the problem of lots of unlabeled data, we can use them to train an unsupervised learning model, generative adversarial networks. In the next example, we will try with optimization functions. SGD, stochastic gradient descent, and momentum equals 0.9. Nesterov accelerated gradient. Atagrad. RMS prop. And finally, atom optimization. Visualize the convergence speed between the above optimizations. The best is Atom. Next, avoiding overfitting through regularization. Choosing L1 or L2 regularization will depend on the initial lambda parameter. Usually 0.01 will be chosen. Finally, dropouts are added after each layer.